if Andre is right, this is really important, but he can't be right. I mean, everybody would know that, and nobody I know knows about that. Next morning, one of my students brings me the book, the 3 books of lectures by the great Nobelist Richard Feynman, and there it is. He opens it to Volume 2, Chapter 9, and Volume 2, Chapter 9 is a full chapter about the Earth's electric field and the negative charge of the Earth, along with all the evidence for it. So, so it's there. It's just that we don't know about it. We didn't know about it, and it's true that the American educational system is, at least in that sense, deficient because it doesn't talk about this. It's as though, yeah, it's okay. 50 years ago, some people made measurements, but it's not so important, so we just won't include it in the textbook, and so we don't learn about it. Anyway, that's sorry about the long introduction, but if you connect yourself now electrically to the negative Earth by so-called earthing or grounding, it allows the electrons from this vast, practically infinite sea of negative charge to seep into your body and build easy water. And I think that is perhaps the reason why people have recognized that connecting to the Earth is really important for health. And if you do it on a regular basis, it should be good for health. And I know companies are building gadgets, devices to make it easy for you to connect yourself to the Earth. And there are lots of reports that show that it works. So this is another way of building easy water and contributing to your health. Was that the end of your question, or?
Yeah, that's. I think Star has a question.
Well, connected to that, you sort of were skirting around, and you didn't say the word nature, because we have within us these vehicles that we are in are designed to do that, to make that connection with the negative charge of the Earth.
Sure.
And and so you also were talking about this. You brought in talking about the spring, natural spring water, and the ways that the eddies and the flows in a river and in a creek and a stream, that those change also the water, right? So
yes.
And so also then I heard in the back of my head, I heard someone thinking, okay, if infrared is all around us, why isn't all water easy water? And it must be because of how much energy it requires to change the molecular structure to that hexagonal shape.
Well, let me respond to that one. Again, a whole long series of concepts and ideas, and by the time I answer one, I forget the other. But you're right. There's a lot of infrared energy around, and if you supply enough, in theory, the easy should build up, and all water should be easy, but not quite. We did an experiment that shows that that's not the case, and that is what happens is, as the easy grows, it's negatively charged, and the protons. Remember, all this happens because water is broken into OH minus, which forms the easy, and H plus protons, which fill the rest of the water, the bulk water. So we found that if you get too many protons in the bulk water, the easy stops building. And we did a very simple experiment to demonstrate that. If you compare easy buildup in a small petri dish versus a large one. In a large petri dish, those protons have an opportunity to spread all over the place. They're not so concentrated. In a small petri dish, the protons are pretty concentrated. And so we found if you try to grow the easy in a small petri dish, it's smaller. If you try to grow it in a big petri dish, it's bigger. And we concluded that at least probably, we think, hypothetically, that when the proton concentration gets too big, the easy won't build anymore. And it might be that those protons will start penetrating back into the easy, and it just reaches a point where it can't grow anymore. So no, all water, at least we have seen no example, except one I'll tell you about in a second, where it's all easy. And I guess I wanted to tell you about another because it's rather striking. This was not our finding, but we've confirmed it and extended it. It is that it's the finding of Vittorio Elia from Naples, a very experienced biochemist. He found that you can take easy water and you can create from the water, which is a liquid or liquid crystal, you can create a solid, kind of like a powder, a solid substance at room temperature. It's pure easy. I'm not sure if you're aware of this. He has a few publications on it. You can take it and you can put it in your hands and feel it. It looks like a kind of fragile thread that's wound around. And if you put it in your hand, it quickly will disintegrate into a powder, but it's stable at room temperature. And if you take this stuff, we did experiments that we're just writing up manuscript now to confirm and extend, because it's such a brilliant finding. I think, imagine a kind of water that's a solid at room temperature. Solid water at room temperature. It boggles the mind. So we tested it. And the first thing we tested for is if you take some of this powder and you put it back in water, does it create easy water? And we confirmed that it does. It absorbs light at 270 nanometers. Wow. But further than that, we used a mass spectrometer. We're collaborating with someone who is very experienced in that to check to see whether there are any contaminants. A lot of people like to say, whatever you found, it doesn't matter what you found. Oh, it's caused by contaminants. It's a very it's an almost reflexive kind of comment. And with the mass spectrometer, you can tell what substances are in there. And we did with 3 separate examples of ways of creating this solid, easy water at room temperature. And in each case, there's no possibility from the measurements that this is caused by any kind of contaminant. It's real. So from that and the absorption of light at 270 nanometers, we think this is real, and it's exciting to be able to take this stuff and make a solid out of it. I can imagine interesting applications of this for the future. So yeah.
But will it hydrate you?
It gives just add water a whole new meaning.
Yeah. Will it hydrate you? Well, I take the fifth on that. It may absorb some water from the rest of your body, and if it absorbs bulk water and turns it into easy water, more easy water, maybe yes. See, hydration, we use the term hydration. Everybody uses the term loosely, but I think of hydration as filling the cell with easy water. And by the way, just stop me if I'm going too far on the tangent. No. A lot of people stick electrodes into cells, and they always measure negative electrical potential compared to the outside. Inside is always negative. And you may know that the textbook explanation for that has something to do with the membrane, gadgetry in the membrane, pumps and channels, which pump some ions out and let other ions in. And that's the explanation for why the cell has a net negative charge. And I think it's dead wrong. I can explain to you why, but I don't know how much time we want to devote to this, but a very simple explanation is that the reason the cell has negative charge is because the water inside the cell has negative charge. The cell is filled with easy water, and it's the same in a gel. If you were to stick the same electrode that you would stick inside a cell and stick it into the gel, you get the same result. Usually, most gels are minus 100 millivolts or minus 150. and have no membrane, and therefore, no pumps, no channels, no nothing, just the gel, but the result is the same. So if you would like to say that the reason for the cell's negative electrical potential has something to do with membrane gadgetry, then how come you get the same result if you have none of that gadgetry? Yeah. So
Right.
again, yeah, simple. But that's a digression.
I know, but let's, there's a couple of questions here that I'm very curious about. You have a company called Fourth Phase Incorporated
We do.
that has been funded, and you were exploring how to make maybe a municipal water supply with easy water with a machine bigger than just a little laboratory model. And
We
how's
do.
that going?
Poorly. Well, sorry. What I should say, I should expand on that. We got to work on that. What we call the filterless filter, and we spent 2 years, and we made a lot of progress on it. And it turned out that there were a few things that we were not able to solve with the investment of money and people that we had, and so it didn't reach the stage of being useful for humanity, and we pivoted to another project, and we had some difficulty, some internal difficulty in the company, and someone has come along, is now purchasing the assets of our company, and that's ongoing right now as we speak. And so I think that in the future, that company will be sold to a different company, and hopefully that company will keep working on it and producing it. And if not, we'll find another way to continue along. So I would like to say that it's just around the corner, but I'm not sure. It's very exciting because it's not just a filter that can separate junk that's in the water, and you get clean water out of it just from the energy of the sun that separates the infrared energy that separates bulk water from easy water. But it also can separate, we think, salt molecules. So in other words, you can start with ocean water.
Wow.
And from the energy of the sun, you can separate the salt from the water, the salt being, you might say, a contaminant. And that way, it may be possible to get drinking water from ocean water. And you can do it now by, as you know, reverse osmosis, but it requires a hell of a lot of energy to do it. But in the situation we're talking about, the energy comes from the sun, and the places where this is needed, like the Middle East, believe me, I've been there enough times. There's a lot of sunshine there. And with a lot of sunshine, it means you've got a lot of energy to do this. And so, although we made only limited progress on the salt separation, I think this is this will be the jewel in the crown of being able to do that. And how long will it take? I'm not sure, but it's very exciting to think about it.
That's great, because you answered like 2 or 3 questions there with one paragraph. Like, what's, well, understanding UV light creates, what do you need to carry on your, I know you probably need some more investors, but you had a substantial one last time I talked to you, but that was like 2-3 years ago.
We've had some substantial ones, yeah.
Yeah, they were great. And, are they still on board with you, or do you want to talk about it?
It's a little bit sensitive because the company is now on just at the edge of the company assets are at the edge of being sold to another company, and
Okay.
so maybe it's not appropriate to. But we're all, if that company doesn't pursue it, we will find a way to pursue it.
You always do.
When you say find a way to pursue it, are you talking about the Venture Science Foundation?
No, this is something different. I'm glad you mentioned it. You're talking about the Institute for Venture Science.
Right.
And this institute doesn't deal with technologies at all. It deals with fundamental science. And this is an institute that we founded a few years ago. It's still in the build-up phase, and the idea is to fund promising ideas that challenge conventional thinking, especially where conventional thinking simply isn't working. You know, then it seems logical to, you know, instead of your brick wall reminds me, instead of beating your head against the brick wall, you know, try something softer or
Go in another direction.
another direction instead of doing it. And while there is money here and there to pursue technologies, there's not a whole lot of money to pursue radical ideas that challenge convention and fundamental science.
Right.
You certainly don't find it in the government, and you don't find it so much in most private foundations. And so we're creating an opportunity for someone like you, maybe, or, you know, like Owen or whatever. You got an idea in fundamental science, and you want to pursue it. And you apply to our institute, and we evaluate your project. We evaluate it with a very thorough vetting process that involves, if you're, for example, Jim, your idea is the first criterion is this an idea if it proves to be adequate, valuable, will it really shake the earth? Or is it trivial? So you get a high score if it will shake the earth, if it's right. And then we ask the question, well, what's the track record of this guy? Does it look like he's the kind of guy, or she's the kind of woman, or whatever, who's likely to succeed in this? Is it just in the brain, or is this someone who can actually do something to make it work? And we have already identified 5 projects from more than 200 pre-proposals and 15 subsequent proposals. We have 5 projects that are ready for funding, and they're all extremely interesting. And we have some funds available, but we're looking for really major kinds of funding from private individuals who have done well. You know, and a lot of people, I know a lot of people who've done well, and they're looking for meaningful ways to contribute to society, and they don't know where to put their money. You know, should I put it into American Cancer Society, or to the American Heart Association, or whatever, or what? And we would like to encourage people to look into the Institute for Venture Science, because I think we have something that is going to shake the earth. You know, if you think about where science is going and how many really important fundamental scientific revolutions we've had in the past, I don't know, 30 years or so, you'll find a lot of technological revolutions, like being able to Zoom today. But in terms of fundamental scientific revolutions, I would challenge you to name even a handful, or even 1 or 2 that have succeeded of high magnitude, like the genome idea that was in 1954, I think, or splitting the atom 10 years before that. I mean, of that magnitude, fundamental science, not technology, because it's not happening. And why is it not happening? The amount of money that's given to the funding agencies, it just keeps going up and up and up. And yet, where are the scientific revolutions? And I think this is a system problem, because it's difficult to bite the hand that feeds you. And the people who are making judgment on whether you should get the money are your competitors. So, you know, if you think the earth is round and everybody else around you, they all know that it's flat. If you submit an application to get money to study round earth because you have some preliminary evidence, you know, you've seen satellite photos, and et cetera, the people who are going to review that application are your competitors. They're the flat earth people. and there's no way that you're going to succeed.
Mm.
So a lot of scientists know that. They just don't bother suggesting anything that's radical that is going to put them in an awkward spot because they won't win.
Well, there was a discovery by a friend of mine named Gerald Pollack here recently that discovered or rediscovered the fourth phase of water.
Oh, that's worthless.
We
That's
don't think
worthless.
so. We don't think so, or we wouldn't be here today. We think it's the biggest scientific discovery of our time.
Oh, you're very kind, Owen. You're my real friend.
Oh, it is. It is.
Yeah, and I'll send you a check for that nice comment.
Well, I'll back him up because I think it is too.
Well, thank you. You guys are great. Well, there's more coming. A lot more coming, and even beyond water. I share. I mean, frankly, I share your excitement because I think there are so many opportunities that come from it. But in most cases, it's not so easy for me to get money either. I got to tell you, we have two private supporters who actually came to us and said, "We like your stuff. We want to fund you." But some people are not doing too well because of COVID, and it's getting tighter. And so we could use some help in the laboratory. I mean, quite apart from the company or apart from the Institute for Venture Science, in our laboratory, we could use some help to continue on. It's so exciting. I mean, we've got a lot of good stuff happening.